All right, good day, one and all. This video is being made to explain lab activities for week 7. This material is being done by the GPAC Academic Board as a supplementary material, not an alternate material. For any further clarification, kindly see any member of the GPAC Academic Board. With that being said, let's start. All right, so week 7 is about oxidation reduction titration. We started that in week 6, and then we are doing the second part in week 7. Week 6 focused on using KMNO4, right? Now in week 7, we are doing iodine titrations, right? Good. So, as we always know, before we use any reagent at all in a titration, we first standardize, right? We standardize against a primary standard. After the standardization, we understand that what we have here to use in our further titration is called a secondary standard, right? Good. Then after learning how to standardize, we use our secondary standard in determination of the strength of melting, and then we also work the determination of volume strength of hydrogen peroxide, right? Good. So this is the second method to determine the volume strength of hydrogen peroxide. You can use the KMNO4 to do it, and then you can also use iodometry to do it. Very simple. Good. So oxidation reduction titration, iodine titrations. Now we are seeing iodine as a mild oxidizing agent which can be used in neutral solution. Now the iodine we are talking about here, for clarity's sake, is I2, right? So always when you hear the iodine, think of the I2. Good. Now we are saying it's a mild oxidizing agent. That means it can cause oxidation and then itself will be reduced. So if we say it can cause oxidation, it means it can increase the oxidation number of a certain atom, but then itself as the iodine at the end will be reduced to I-. That is the whole idea, right? Good. And then we are seeing that it is insoluble in water, but readily soluble in a solution of potassium iodide. Hence, it is prepared in a solution of Ki. It forms complex with Ki according to the equation. So this is a very simple equation showing how iodine can be solubilized in Ki, right? Good. We are seeing iodine itself, it's not soluble in water, but then when you add it to Ki, because of the formation of this complex, right, it becomes soluble, right? Something for us to keep. But then we'll not really apply this directly in any of the calculations that we'll do. Now we are seeing the reducing agent used extensively in iodine titration is sodium thiosulfate, and it reacts with iodine according to the equation. So this is a reaction between sodium thiosulfate and then iodine. Now the most important thing here, if you have been following our discussion, is the mole ratio, right? Always we are looking at the mole ratio. That becomes the most important parameter. That is not to say you are not supposed to learn how to write the reaction. You are supposed to learn how to write the whole reaction here and then balance it, right? Good, because in your presentation, you have to write the reaction, balance it before you can quote the mole ratios and use in your calculation, right? Good. Now you are seeing there are two distinct classes of iodine titration. We have the iodimetry, which is direct iodine titration, and we have iodometry, which is indirect. Good. Now let's look at the dichotomy between the two. Now in direct titration, which is direct iodine titration, iodimetry, we use a standard iodine solution. So we present you with an iodine solution, and then that solution is directly it's reacted directly with the substance being oxidized, and the amount used is determined by direct titration or by adding excess iodine and back titrating with sodium thiosulfate. So this is how we do iodimetry. We use standard iodine solution. So we have the iodine solution already, and then we use it in the titration, right? But then in the indirect, which we'll be talking about in this discussion, I mean, everything we'll do will be about indirect. What we do is that we don't have the iodine, the I2 readily available, but then we have a reaction that will release the I2 in situ. Now, when the I2 is released, then it goes ahead and reacts with the thiosulfate for us. I hope we are following. So that is the idea. And so if we read, we are saying that in indirect titration, iodine is liberated from potassium iodide. That means what we have initially, we don't have I2, we have I minus, right? So we need an agent, which is an oxidizing agent, to take it from the I minus to the I2. So the I2 is produced in situ, and then the I2 reacts with the sodium thiosulfate in the reaction that we've already talked about, right? Good. And then we can do some quantitative calculations from there. Good. Now we are saying iodine solutions are sufficiently intensely colored to act as their own indicator. However, it is more useful to use starch as indicator, right? Good. So the indicator we use in iodimetry is starch. Standardization. Now, always this is the first thing that we do. We want to correct the concentration of the sodium thiosulfate that we use. We cannot just go by the concentration which is written on the bottle or which has been presented to us. We have to get a factor. So always when you're doing your standardization, you are looking for a factor. And the factor you get can be used to correct the concentration of your secondary standard, and it can also be used to correct your average titer, right? These are the two importance of your factor from your standardization. Good. Now, the primary standard that we use, that's the oxidizing agent that we use in iodometry. The common one is potassium iodate. So we are saying annular potassium iodate is a powerful oxidizing agent used as primary standard to standardize sodium thiosulfate solutions. Now, in the standardization of sodium thiosulfate, which is the titrant, potassium iodate, that's the primary standard, liberates iodine from potassium iodide by oxidation in the analyte, and the amount of iodine liberated determined by the titration of the sodium thiosulfate. So, I mean, the long English we are saying describes what we talked about in the period. That's in iodometry, we don't have the iodine readily available. We don't have I2. What we have is I minus. So we need, now the I minus here is coming from the Ki. So in solution, the Ki will dissociate to produce K plus and I minus. So this is where we are getting our I minus. Now, the primary standard would convert or would take this I minus. The proper term is oxidize. So oxidize I minus to I2. After producing the I2 in situ, then it can go ahead and react with the sodium thiosulfate. So that's what we are talking about. That's the whole thing we are talking about here, right? Now we are seeing potassium iodate oxidizes the iodide to iodine in acidic solution according to the equation. So this is it. Sodium iodide. Sorry, the potassium iodate converting the iodide to the I2 that we need. Now, from whatever I've said so far, I realize that in this standardization that we require two steps. The first one is the oxidation by the potassium iodate. Then the next one is when the iodine that we have produced here, right, reacts with the thiosulfate. And so what we need is that we have to be able to write this equation, but then this is not the mole ratio that we will use, right? We would combine that with the next equation to get an overall equation, and then we'll use the mole ratio from the overall equation to what? To do our calculation, right? I hope we are following. Good. So let's look at what we'll do in the lab, and then we'll go ahead with some calculations. So standardization of sodium thiosulfate solution, lab activity. Prepare the solutions of sodium thiosulfate pentahydrate and potassium iodate. And pipette 25 ml of the potassium iodate solution into an iodine flask or conical flask wrapped with black polythene bag. Very important because iodine is photosensitive, right? Good. And add about 1 gram of potassium iodide and 5 ml of 1 molar H2SO4 solution, and titrate with sodium thiosulfate titrant until the color of the analyte diminishes to a faint straw color. Add 1 to 2 ml of starch solution as indicator and continue the titration to the end point, blue to colorless. Repeat the determination twice to obtain the determination results. So this is what we'll do in the experiment, in the lab during the experiment, and I'm sure the experiment will familiarize us with this procedure. Now let's look at the calculations. Good. So this is a sample question, and then they have already done the titration for us, so we just have to do our calculation. Now let's read it. In a laboratory exercise to standardize a prepared solution of 0.015 molar sodium thiosulfate solution by iodometry, Isaac pipetted 20 ml of a solution of potassium iodide in an iodine flask. He added about 1 gram of potassium iodide and 5 ml of 1 molar H2SO4 solution. So I didn't underline these parameters because they will not be used in your calculation, right? Yes. And titrated the resulting content with sodium thiosulfate until the color of the analyte solution diminishes to a faint straw color. He then added 1 to 2 ml of starch solution indicator and continued the titration to the endpoint. Replicates determinations were subsequently carried out twice to obtain the results below. So this is everything, the 3 determinations here. Now from the table, what we do is that we find the titers and then we come to find the average titer, right? So the 0 from this one is still 21.70. This one should be 21.80, and the last one should be 21.90. So we add all these 3 and then divide by 3 to get our average titer. Now, once you get your average titer, you are done with the usefulness of the table, right? Let's look at the questions. We are asked to calculate the factor of potassium iodide. Now, the potassium iodide is the primary standard. We all know this is how we calculate the primary standard. It is the actual weight over the expected weight. Now, we are not doing the experiment, so they give us the actual weight here, which corresponds to the 5 liters of primary standard solution, right? So this is the actual one that we weighed in the lab, right? Now, for the expected one, we'll get it from our equivalent calculation, right? Now, right after getting the factor for the primary standard, we can get the factor for what? The secondary standard. That is, we say C1, V1, F1 is equal to C2, V2, F2. So this is it, right? Now, because always we understand that the concentration of the primary standard is the same as the concentration of the secondary standard, such that if I'm telling you that solution we are using is 0.015 molar sodium thiosulfate, it means the primary standard, which is the potassium iodide, will be prepared to have the same concentration of 0.015 molar. And so usually the C1 cancels the C2, and so we have V1 F1 is equal to V2 F2. So there's the equation that we use to find the factor. So right after finding the factor here, we can just find the factor of the secondary standard. Then after that, we are supposed to find the actual concentration of the thiosulfate, which is so simple because the actual concentration becomes the concentration that we think is here, right? This is the expected concentration times the factor. That is why we said the factor is used to correct the concentration. Good. Now let's look through the solution. So they've beautifully found the average titer here. We've discussed how to find the average titer. Now, from whatever we have said so far, you realize that the iodometry occurs in 2 steps. The first one is when we are liberating iodine. The second one is when the liberated iodine reacts with the thiosulfate, right? So this is the first step, this is the second step. But then what is important to us in this experiment is the overall reaction, because it is from the overall reaction that we will get our mole ratio, which will help us in our equivalent calculation, right? So this is the overall reaction. And depending on what we are told, we can keep this or not, right? But then the most important thing that we need, that we can't do without, is the mole ratio, because we need the mole ratio in what? In our equivalent calculation. So we write that the primary standard expressed in mass in 1,000 ml is equal to 1 molar of what? Of the thiosulfate. Then we correct this equation using the mole ratio. So what? 1 times this and then 6 times that, right? Good. Then after correcting, we get our proper statements as we have here. We step down the concentration, the 6 mole here, 6 molar here to 1 molar by dividing by 6. Then we do the same thing to the mass. Now we further step it down by multiplying by 0.015. That has been done here. And then you multiply this side too by 0.015. Whatever you do to this side, it affects the mass side, right? Good. Then the next step, we step up the volume to 5 liters, right? By multiplying this side by 5 and multiplying the mass here by 5. So this becomes the end of what? Our equivalent calculation. And this mass here is the expected mass. Now, we had the assay, so we had to correct the mass gotten from the milli equivalent using the assay, right? And so if 100% corresponds to this, 99% will correspond. So we scale it up a little bit. Now this becomes our proper expected weight. Good. Now after getting this expected weight, the corrected expected weight, the factor of the primary standard is equal to the actual weight over the expected weight from the milli equivalent, from the equivalent calculations. So this was given to us in the question. This was stated in the question for us because we are not doing the experiment. So they give us the value, and this is what we calculated from here. Now, if you divide, what you get will be the factor. So from this, our factor is 0.9926. 0.9926. Good. Now, factor of the secondary standard. The formula they have used here is F1, F2 is equal to V1, V2. So that's what we've used. And then they have made the factor of the thiosulfate the subject of the equation. Good. Now, quickly, so we have the factor of the primary standard multiplied by the volume of the primary standard, which is the volume of the pipette, right? The primary standard is the analyte that is pipetted, right? Divided by the volume of the thiosulfate, which is the volume of what? The titrant. That is the average titer. So we are using the average titer here. And then that will produce the factor of the thiosulfate for us. Good. So we are almost done with this. Now, the last question is asking us to find the actual concentration. And the actual concentration will be the expected or the nominal times the factor, right? So this is what we have times the factor, and then we are getting this. Now, it means that this is what was stated as the concentration of the thiosulfate. But in actual sense, this is the concentration of the thiosulfate. It is 0.014 molar. Determination of strength of melting. Melting is a preparation containing 1% sodium hypochlorite in a solution of sodium chloride. It is used as an antiseptic and also to sterilize articles, especially babies' feeding bottles. Sodium hypochlorite reacts with iodine according to the equation. So, I mean, whatever information is up here, we want you to appreciate the reason why we are doing this. What is the importance of melting? So, I mean, that's the reason why we are considering this product, or working on this product. Right. But then our calculation, this is the first thing that we have to keep in mind, the reaction. Now, this reaction if you study it very well, you realize that the sodium hypochlorite is reacting with a Ki, right? With the I minus here, and then it's liberating the I2. Now, this reaction is liberating iodine in situ. That is the whole idea. That is an indirect, we are not using iodine solution, but at the end of the reaction, we are producing iodine. And then the amount of iodine produced can be gotten by reacting with what? The sodium thiosulfate. So it's consistent with the iodometry that we discussed, right? It is so consistent with it. That is why we employ iodometry, right? Good. So this property about sodium hypochlorite makes it appropriate for us to use iodometry to quantify it, because we know that when the hypochlorite reacts with iodide, it liberates iodine, right? And then we can get the amount of what iodine liberated by reacting with what the thiosulfate. So the liberated iodine in the analyte is then titrated with the sodium thiosulfate using the starch as indicator. Now let's look at what we'll do in the lab. So we pipette an amount of the concentrated or undiluted melting to make 100 ml solution of diluted melting using a 100 ml volumetric flask and distilled water. So usually we dilute to enhance mobility of ions, right? So ion mobility, that is usually why we dilute. The next one, we pipette an aliquot of the dilute melting solution into a conical flask or iodine flask. Add 1 gram of potassium iodide and 5 to 10 ml of 1 molar A2SO4 solution. Titrate the resulting analyte content with standard sodium thiosulfate solution. Now let's take the sample question. In the determination of the strength of melting by iodometry, AMA pipetted 25, always the pipette volume is very important, 25 of the undiluted melting. So that means the undiluted one is 200 ml, right? To make 100 ml using a 100 ml volumetric flask and distilled water. She took an aliquot of 20 ml from the dilute solution and transferred it into the conical flask. Added about 1 gram of potassium iodide and 5 to 10 ml of 1 molar A2SO4. She then, so I have to underline this because this will be very important to us. But then the 1 gram of iodide and then the 5 to 10 ml, this will not be used in our calculation. She then titrated the resulting content with standard 0.015 molar sodium thiosulfate using iodine starch as indicator. Replicate determinations were subsequently carried out twice to obtain the results below. Good. Now, let me take time and explain the dilutions here so that when we are doing the calculations, we understand. Good. So the first one, now there was a concentrated solution, right? An undiluted one. And then we took 25 ml. So that was the first thing we did. We took 25 ml and then we diluted to 100. And so if you are with me, you would understand that the amount of substance in 25 ml will be the same as the amount of substance in the 100 ml. Because if, let's say, there were 10 particles in the 25 ml, right? What we did was that we added water or an appropriate solvent to get the volume to what? To 100 ml. But still, there will be 10 particles inside. The particles will not increase. And so at a point, they will make you find the amount of substance in what? In 25 ml, in the 100 ml of the diluted. Then they will ask you to find the amount in 25 ml of the undiluted. It will be the same thing, right? So that is the first thing that we have to note about these dilutions. Good. Then from the 100 ml, which was diluted, she took 20 ml, right? Good. So let me go over what I said again. So for this 20 ml like this, if I can extrapolate, right, and then get the amount in the 100 ml, this amount in 100 ml is the same as the amount in the 25 ml here. It's the same as the amount in the 25 ml here. just because when I took the 25 mils, all that I did was that I diluted to the 100 mils, right? So the amount of substance in the 25 mil will be the same as the amount of substance in the 100 mil. Right? That is the understanding that we have to get here to make the question very simple. Now we have our table. Always when we have our table, we do our subtractions. And then we get our average titer. We look at the calculation for the average titer in the next slide. Then the question that we have here, we are supposed to calculate the molarity of the hypochlorite in the diluted solution, and then we have to get the percentage of sodium hypochlorite in the undiluted melting. So first we are looking at diluted solution. We are getting the molarity for diluted, and then now we are getting the percentage. Second one, percentage for the undiluted. They have given us the molecular weight and the factor. And the factor was the one that we calculated initially before we started the standardization, right? Good. And then always remember the factor is used to correct the average titer and then the concentration. So in this example, you see the factor being used to correct the average titer here, the average titer. So always keep in mind that right after getting your average titer, the next thing is to correct it. And then what are you using to correct it? The factor to correct it, right? Good. Let's move on. So this is the calculation for the average titer. We got 4 mils. The next thing that we did was that we corrected it. So the average titer multiplied by the factor will give us the actual volume. Right? So that is the correction that I'm talking about. Always after getting your average, multiply by the factor to correct it. Next up, equation, right? So this is an iodometry. Always the reaction occurs in 2 steps. The first one is liberating the iodine, and then the second one is the iodine reacting with the thiosulfate. Usually, as I told you, we get our mole ratio from the overall reaction, right? We get it from the overall reaction. This is where we get our mole ratio. And this, we use our mole ratio to get or establish our equivalent calculation. So with the equivalent calculation, the mass of the hypochlorite in in 1,000 ml is equal to 1 molar of the sodium thiosulfate. We correct that with the mole ratios here. Then we step the concentration down to the concentration in the question. We step the volume down to 1 ml. So this is milli equivalent calculation because we are stepping it down to 1 ml, right? Then we get our corresponding mass. Now let's read this. Now this means that every 1 ml of the 0.015 sodium thiosulfate solution introduced into the analyte neutralizes 1 mole of iodine liberated from the oxidation of potassium iodide with 0.0006 grams of sodium hypochlorite. Now, whatever they are saying is that if you get this, it means this amount, 1 ml of this, the sodium thiosulfate reacts with this mass of the hypochlorite. It's not a direct reaction, it's an indirect reaction actually, because we are doing iodometry. But then in essence, whatever we are seeing here is that after establishing your milli equivalent calculation, right, 1 ml of the secondary standard here, the one you use in the titration, 1 ml of it reacts with this mass of the hypochlorite. So that is what we use. So that's the statement that we have established here, that if 1 ml of your sodium thiosulfate reacts with 0.006 grams of your sodium hypochlorite, then the average titer, the actual volume, the corrected one, will contain what? Right? Now, right after getting the amount, so this is just proportion, use proportion to get your answer. Right after getting the amount here, now the amount here is the amount that was in the volume you pipetted. So that was in the 20 mils that we pipetted. So that is the understanding, right? Good. Then quickly, after getting what is in the 20 mil, then they asked us, we realized that we took the 20 mils from 100 mils. So we try and then we find the amount in the 100 mil. So the amount in the 100 mil is proportion. If the 20 mil contains this, and the 100 mil will contain, do our proportion, we get 0.01 gram of the hypochlorite. That is the amount in the diluted 100 ml. Now, I've already explained that that amount in the diluted 100 ml will be the same as the undiluted 25 ml. So that's what has been stated here, that the undiluted 25 ml contains the same amount, right? Good. Then they asked us to find the molarity. Molarity is moles per liter. So first of all, we have to convert it to liter, right? So we took it from here that and then we are doing it for the diluted sample. We are doing it for the diluted sample. So if the 100 ml of the diluted contains this amount, then 1,000 ml of the diluted should contain what? So this will give us the mass. This will give us the mass, right, in 1,000 ml for the diluted. But we are not looking for mass. We are looking for what? The moles in 1 liter or in 1,000 ml. So we divide. This is the formula. P is equal to MC. P is equal to MC is the mass density. That's what we, mass density is equal to the molar mass times the concentration. And from this, you realize that the concentration is equal to the mass density all over the molar mass. So that's the formula that has been used here. Right? This is the mass density 0.1 divided by the molar mass. That was given in the question, right? 74.5. And then you get this. Right? So this is the molarity of the melting. Now, the next question asks us to find the percentage concentration for the undiluted. So the undiluted, from here, we understand that 25 ml contain this amount of the hypochlorite, right? So therefore, 100 will contain what? Now, after getting what the 100 contains, we state it as what? Percentage weight in volume. So that is it. So we have 0.04 percentage weight in volume. Percentage weight in volume simply means the amount in grams, the weight in grams in 100 ml of what solution. So that's what we have established here. Very simple. Next up, determination of volume strength of hydrogen peroxide, iodometry. Good. So we are saying that the determination is based on the reaction expressed by the following equation. Now, the hydrogen peroxide plus 2 moles of H plus 2 moles of I minus react from I2 plus 2 moles of water. Now, this step is similar to all the first step that we have done in iodometry, a step where we see iodide being converted to iodine, right? A step where we see oxidation of iodide, a step where we see the release of iodine in situ, such that the amount of iodine released here, right, can react with the sodium thiosulfate. And then when we get the amount of iodine, we can use it to get the amount of peroxide that exists in the preparation. So that is the whole idea. So it follows the same rationale that in iodometry, we are looking at, and in that we don't have the iodine upfront, but then we can have a reaction of the compound that we are using that will release iodine, and then the iodine release can be reacted against what? The thiosulfate. That is the whole rationale. So this is the first step. The next step will be when the iodine here reacts with the thiosulfate, and then usually the mole ratio that we use in our milli equivalent calculation should be the overall reaction. Now, there's a statement here which says that the reaction is relatively slow, but the rate increases with increasing the acid concentration. So, I mean, if we are talking about the rate increasing with increasing the concentration of acid, the substance that increase the rate of reaction, we call them catalyst. So it's a no-brainer here that we are seeing the acid is the catalyst of this reaction. Lab activity. Take a defined volume of a 6% solution of hydrogen peroxide, 20 volume strength, and dilute to 100 ml using a 100 ml volumetric flask and diluted water. Pipette an aliquot of the diluted solution into an iodine flask and add the required volume of acid, H2SO4, and then the required amount of potassium iodide solution. Allow the resulting analyte content to stand on the step for a while and titrate the liberated iodine with a standard sodium thiosulfate solution, adding a 2 ml of starch mucilage near the end point. That is when the color of the iodine has become nearly discharged. Repeats the determination twice to obtain concordant results. So this is the activity we'll do in the lab, and we'll get it clearer when we perform the experiment in the lab. Now, calculations for us. So the exercise, we are saying that during the assay of hydrogen peroxide, Amma took 3 ml of a stock hydrogen peroxide solution whose total volume is 200 ml. And diluted it to 300 ml with water to produce solution B. 20 ml of the pipetted solution B was transferred into an iodine flask, and the required amount of acid and potassium iodide were added. The iodine liberated was then titrated with 0.015 molar sodium thiosulfate solution using starch mucilage as indicator, and the results are shown below. Good. So let's look at something here. Yes. Now the questions are for us to calculate the volume strength of the hydrogen peroxide sample provided. Now, the sample provided is the undiluted one. That means everything we do, we have to go back to the undiluted one. It's just a simple question, but then this is in reference to the original hydrogen peroxide. Good. Now let's look at something in the question. Now, they took 3 ml of their concentrated solution, and what did they do? They diluted to 300 ml. Now, if I'm not afraid, that say that the amount of substance in the 3 ml here is the same as the amount of substance in the 300 ml, because you took it and then you just diluted it, right? And then we took the 20 ml from the 300. So if you can use the 20 ml to extrapolate and then get the amount in 300 ml, then that amount in 300 ml is the same amount in the 3 ml here. Very simple. That is the whole thing. And that is the trick about the question, right? Good. Now we have a beautiful table here. What we do from the table is that we get the average titer. Good. Now they have given us a factor here from standardization. What would we do with the factor? We correct the average titer using the factor, right? We correct the average titer using the factor. Then they have given us, okay, the molecular weight of peroxide 2. Good. Now let's go through our solution. So we calculate our average titer. We correct our average titer. So we have gotten here. Then this is the first step, first reaction of iodometry. This is the second reaction, but always the overall reaction is where we get our mole ratio from. So this is the overall reaction. 1 mole of A2O2 corresponds to 2 mole of Na2S2O3. So that's it. This is it. This is it. Good. Then we'll use this in our milli equivalent calculation, right? So after the milli equivalent, we are getting 0.0003 grams of hydrogen peroxide, corresponding to 1 ml of the 0.015 molar Na2S2O3. So this is what we have here. Now this means that 1 ml of the thiosulfate reacts with this mass of peroxide, right? So if 1 ml reacts with this, then the average titer reacts with what? So we'll do our proportion here, and then we get 0.0125 grams. So this is what we have gotten, right? Now, this is the amount of the peroxide in your pipetted volume. In your pipetted volume, that is the 25 mils. I'm sorry, the 20 mils here. That means the 20 mils of your pipetted volume contains 0.0125 grams of peroxide. I hope you are following. Now, the weight of the peroxide in the 300 ml of diluted solution of peroxide. So if 20 mils of the diluted solution contains this, then the 300 ml. So this is a simple proportion. We get the amount in the 300 ml. Not forgetting that the amount in the 300 ml is the same as the amount in the 3 mils. Same as the amount in the 3 mils. Good. Now that is what has been stated here, that the amount in the 3 mils is the same as the amount in the 300 mils, right? Good. Now we are supposed to now calculate the volume strength. The volume strength. So the volume strength, we start writing the reaction. This is decomposition of hydrogen peroxide. So hydrogen peroxide would decompose to produce 2 moles of hydrogen peroxide decompose to produce 2 moles of water, and then 1 mole of what? Oxygen. So that the mole ratio has been stated here. The mole ratio has been stated here. Good. Now, per the mole ratio, we can correct. So the 34 grams of hydrogen, that was 1 mole times the 2, that is the mole ratio here, right? Will give us 68.000 grams. Will correspond to the molar volume at STP, molar volume of what? Of oxygen. Now, what would the weight in 1 ml stock, the 1 ml be? So then it means we have to take it from the 3 ml stock to 1 ml stock, right? That is simple proportion. We take it from the 3 ml to 1 ml stock, and then we get 0.0623 grams of the peroxide. Good. So that is what we have. This is it. Very simple. Good. And the volume strength of the hydrogen peroxide. Okay. Good. So finally, then we come and put it here. So we are continuing from here. And we've realized that 1 mole of the stock contains this mass. So then the 68.00 gram of the peroxide corresponds to the molar volume. That is the 22400 mils of oxygen. Then this one, 0.0623 grams of the peroxide will correspond to what? Now, this is also saying that because this amount is in 1 ml of the peroxide, right? So this is indirectly getting us the amount of oxygen that can be what? That can be produced by 1 ml. That is what is getting us. So that is the meaning of actually the volume strength, such that if the volume strength is 20.5, as we have gotten here, now we are saying that if you take 1 ml of the solution, it will give 20.5 ml of oxygen gas, right? If you take 2 ml, it will give 41.0 ml. And so always, if you take any amount of what the peroxide preparation, it gives you this times the volume strength times the oxygen or the amount of oxygen, right? So for me to have gotten the 41, I had to just multiply the 2 by the 20.5. That means if I am supposed to pick 10 mils of my hydrogen peroxide stock preparation, it will liberate 10 times the volume strength, which is the 20.5. So that is the whole rationale behind this calculation, right? Very simple. Yeah, I think this is the last thing we have to talk about in regards to week 7 lab activity. As I said, this is a supplementary material, not an alternate material, done by the GPSA Academic Board. If you have any issue at all, kindly contact any member of the GPSA Academic Board. Thank you very much. All the best.